This is section 13.4, and this is examples 4 and 5 in our notes. We're going to evaluate this line integral using Green's theorem, and you can see that it's kind of an ugly looking line integral, but we're just concerned with the derivative of p with respect to y, which is going to be 3, and the derivative of q with respect to x. And that is 7. So with Green's theorem, we have a pretty easy integrand. It's just going to be 7 minus 3, which is 4. Now, the region is the circle with a radius of 3, centered right at the origin. So that's going to be our region D. And our integral will be the double integral over D of 4, 7 minus 3, times dA. Now, if you remember, we talked about this a lot with chapter 12. If we have an integral that has an integrand of 1, so in other words, if we factor out this 4, we have this double integral with a function of 1, okay? That is actually just the area of the region. So in other words, this double integral right here is the area of that circle. Remember when we had a triple integral with a function of 1, that was a volume. So it takes that double integral, and instead of that double integral being a volume, it's actually an area because the function we're using is just 1. So in other words, we have 4 times the area of this circle, which is going to be 36 pi. Now you could do this the long way. You could set up the double integral. You might want to convert that thing to polars. This is a much faster process. So that's example 4. Okay, let's try example 5, last example in this section. So we have the line integral, and C is going to be this boundary between the two circles. So we have a circle with a radius of 2. This won't be probably a very good sketch, but that's okay. So this is going to be a radius of 2, and then we have a circle with a radius of 1, and we're looking at the upper half plane between them. So in other words, what's happening is that we're traveling in a positively oriented pattern around this little region here. Looks like that. So it's kind of this goofy looking region. And our p value is y squared. So dp dy is going to be 2y, and q is 3xy, so dq dx is going to be 3y. So what this means is that our double integral over this region is 3y minus 2y dA, or more simply, it's going to be just y dA. Okay, not quite as easy as the last one because our function is not simply 1. However, in this case, we can convert this to polars and make it a little bit easier on ourselves. So let's let our angle go from 0 to pi, just because we're dealing with just that upper half plane. Our r value is going to go from 1 to 2, and then our integrand, remember, is just y, but y is the same thing as r sine theta. And don't forget, we got to multiply by r, so we're going to make that r squared, and then we have dr d theta. Again, all of that stuff comes from chapter 12. Everything I just did there, aside from this initial setup, all of the initial setup is Green's theorem, and that's chapter 13. The rest of it from here is just chapter 12. Okay, we can split these up, so we can go from 0 to pi of sine theta d theta, and we can multiply it by the integral from 1 to 2 of r squared dr. If you remember, we talked about this a lot in chapter 12. The area of sine of theta from 0 to pi is 2. That's just a constant that we can memorize. You can do it the long way, that's fine. This one is 1/3 r cubed from 1 to 2. That gives us 8/3 minus 1/3. So that gives us 7/3. And what we're going to do then is we're going to multiply that by 2. Again, we're just multiplying these two integrals together, so we get an answer of 14/3. All right, that is section 13.4. You are done with Green's theorem.